Namaskar my dear friends. So we have already seen Ethernet PHY design and detail. We have seen a lot of terminologies that are involved in Ethernet PHY connections. So now we'll try to understand what are the different things that we should do regarding this particular IC, which is DP83826. So as you can see, quickly walk through that. So we had seen the Ethernet PHY internal diagram and how it is connected to our Mac devices and then to the network in the particular block diagram. And quickly we had also seen the details of our pin configurations of this particular Ethernet PHY ICs, like what are the control lines, or RD plus RD minus differential lines or transmission differential lines, and at the same time transmit and receive lines. So now we have also gone through different terminologies like what is my MIIs, RMIIs, GMIIs, based on the speed that these terminologies have been evolved. And we had also seen different ports as well, like Ethernet MII ports will be having what are the TXD lines, like 4 lines will be used, or these are the particular items, or these are the particular interfacing that will be there between the Ethernet PHY port and the Mac configurations, right? At the same time, about the GMII as also we have seen, but this is not the scope in our this particular tutorial. And we have RGMII, which is reduced gigabit media independent interface connections. Now we will try to understand this particular IC, which was DP83826, some of the electrical characteristics, so that we can utilize this in our circuits. Okay. So as you can see, I have taken the particular IC DP83826. Okay, there are two versions, one is I version and one is E version. Okay, so as you can see, some of the recommended operating temperature is analog supply will be typically 3.3 volt, so this is fixed. And then supply voltage for IO lines, that is your input output lines, are two levels, one is 3.3 volt, one is 1.8 volt. So our aim would be to work with 3.3 volt. If you talk about operating free air temperature, so that is typically 25 degree centigrade, but as low as minus 40 degree centigrade and as high as 105 degree centigrade it can go. So these were the things. Now if you talk about VDDIO 3.3 volts, so we have a lot of pins like transmit enable pin or transmit data lines, that is D0, D1, D2, D3. Same way we have transmit clock signals. All these things are having 3.3 volt logic levels. Similar to that transmit line, we have receive lines, and then we have management data IOs, management data clocks, and we have LEDs, indicators. All those things are having 3.3 volt logic. Similar to that, we have oscillator input as well, that is logic level of 3.3 volt. Coming to the next parameters, we have IEEE TX conformances. So that is based on 100 base TX, that is your 100 Mbps. 100 base means 100 Mbps speed, 10 base means 10 Mbps speed. So you can see the differential output voltage you will be getting minimum 950 millivolt to maximum 1050 millivolt. So that will be typically basically 1 volt differential output you will be getting. For 10 base TE you will be getting 1.75 volt output. Okay, so this is the thing that we have to understand. Coming back to the power consumption that will be there regarding this particular thing. So for VDD 3.3 I have taken here. So for MII application for 100 base TX data rate, we have 45 milliamperes of current consumption, that's all. So we have very less current consumption. Similar to that, for 10 base T it is reduced to 35 milliamperes. If you go ahead with reduced MII masters, so then in that case it will be again 45 milliamperes, and like that you can have a understanding for other kind of Ethernet port configurations. If you talk about current in VDD IO, so in that same way you can see the current consumption is very less, which is close to 10 milliamperes or even less than that. Okay. Some other parameters in power consumption, if you see, we have power consumption for active mode worst cases. So in worst cases you will see MII 100 base TX is 44 milliampere typical values, and similar to that other parameters are also there. So these are the things that I have listed out for your understanding, so that you can utilize this particular like data in your power consumption calculation, because power consumption calculation will be very important, because you will be designing the power supply for this particular Ethernet PHY ICs. If you talk about IO signals, so if you see IO signal, we have, let's say, 3.3 volt logic level. In that case, high input voltage will be considered as minimum 1.7 volt. So 1.7 volt will be like seen, then it will be considering as high, otherwise it will not be considering anything. If you low level, if you want, the maximum it should be 0.8 volt, otherwise it will not be able to understand that this is a low signal. So for low signal it should be 0, but maximum it can get as high as 0.8 volt, and it will consider it as 0. If you talk about high level output voltage, so output side it is going to be, that was input side, okay, in output side it is going to be 2.4 volt, and for low level it will be again 0.8 volt. So this is the high level and low level logic levels. If you talk about series resistor for RxD and uh, Rx error, that is basically like receive data lines and receive error lines, and receive data valid lines, receive clock lines, and similar to that transmit clock lines, we have 50 ohm resistors in series. So these are the max series termination resistor, which is already integrated, so we don't need to connect external resistor for this purpose. Now if you talk about the block diagram of this particular IC, so let me open it directly from the data sheet. It will be easy for you to understand in bigger form. Alright, so if we see the functional block diagram of this particular IC, which is my DP83826, so we have to understand the complete functional block diagram, so that we can start understanding what are the blocks that is involved in Ethernet designs. So if you see here, I have opened it from data sheet. These are MII option, is nothing but MII means nothing but it is going to get connected to your, let's say, FPGA connections, okay, or maybe microprocessor connection or ASIC connection, but our main focus is on FPGA, because we are utilizing Ethernet connection in my FPGA designs. So you can see we have transmit clock, transmit enable, then transmit data lines, then we have COL, that is my thing control lines, then we have alright, so we have that is collision detect line, we have CRS, that is your carrier sense lines. So all these things are there. At the same time you can see we have a RX error line, that is receive error line, then receive data valid line. Receive data valid line is actually very important, because it makes you to understand whether the data received is valid or not, okay. Then we have received data transmission line of 4 bits, it is there, and then we have receive clock line. So all these things are actually integrated in your MII RMII interface that you can see here. So this is going to get connected to your Mac device, and between Mac and this particular Ethernet PHY, these are the lines which is acting as a signal transmission line, or control lines, all these things. At the same time, if you talk about RMII option, so RMII option will be having little bit less number of lines. As you can see, we had transmit data lines, 4 number of bits were there. For reduced we have only 2 bits, that is TXD0 and TXD1, and we have transmit enable, and at the same time we have carrier sense line and carrier data valid, carrier sense data valid, and at the same time we have receive data valid, both are together in one single line. Then we have receive error, and then we have receive data line, only 2 bits. So for reduced MII option we have less number of pins for interfacing to the Mac, okay. Now coming back to, so this is again going to the FPGA. So either you can have two option, one is MII option, otherwise another one is RMII option, which is reduced media independent interface option. If you talk about series management, so series management is basically utilized for addressing the Mac devices or Mac addresses, and also these are two wire connections, that is one is management data IO lines and management data clock lines. So management data IO lines will be bidirectional and clock lines will be coming from the MAC to the Ethernet PHY IC. So this is the block diagram that you can see. Coming back to the internal part, so internal part you have two connections. One is two options. One is 10 base T and another one is 100 base TX. So 10 base T is basically 10 Mbps speed and 100 base TX is basically 100 Mbps speed. Okay, so these are the things that is there with that. So this is called nothing but your transmit block. In receive block you have the same options for two speeds for receive block. And you can see we have MII registers. So as the signals are coming inside, we have MII registers, then auto negotiation and wake up on LAN, energy efficient Ethernet and all these things, clock generation, everything is there. Now what is happening is this transmit line, as soon as it is coming from this particular MAC address or MAC device, from there it is going to get connected to the DAC, and this DAC is going to convert it to auto MDIX, and this auto negotiation or auto generation media dependent interface will be sending it to the differential output. So these are the differential TD line and RD lines, right? So these are the things that is happening. At the same time you can see for receive lines what is happening. The received data will be coming through this and then it will be getting through the ADC block. So DAC block is used to change it to the analog function output, and ADC block is used to change it to the digital, and then digital signal will be receiving it through the receive block, and this receive block will be sending it through the receive data line to the your MAC address or MAC devices. So this is the thing that is happening. So what is the flow that you can understand now? The transmit is coming from the MAC device, that is getting connected and going through the DAC, and then it is going to the analog signal as differential outputs to the RJ45 connector. So this will be RJ45 connector that will be connected to the Ethernet. Same way the received interfaces or received differential signal will be received here, and through the MDI operation it will be decoded and then send it to the ADC block, and this ADC block will be converting into the analog signal digital signal, and then after that it will be sending it to the digital outputs to the MAC device. Okay. So these were the complete complete block diagram of this particular IC. Now if we talk about next options, what we have is we have already seen this particular block diagram. Now there are a lot of Ethernet connections that is there. So let us say we are going to utilize this particular Ethernet IC as a repeater. So RMII repeater in master and slave mode will be there. So let us say this is working as my master, and this will be working as slave. Okay, so two ICs are being used, two Ethernet ICs are being used. So one is acting as a master, another one is acting as a slave. So as you can see, RMII means reduced media independent interface. So we have only two pairs of two lines, so TXD0, TXD1. Similar to that we have RXD0 and RXD1. So two lines are there. So master will be receiving through TXD line, and slave will be receiving through this TXD line. Okay. Now why it is called master and slave is because the clock is being sent from the master to the slave. So as you can see, we have crystal oscillator input, so that is nothing but the clock input coming from the master device, and master device clock input is actually taking from the crystal oscillator of 25 megahertz. So this 25 megahertz crystal oscillator is generating the clock signal for this particular master device, and then after PLL operation and all, you will be sending 50 megahertz signal to the slave device. Okay. So this is called as RMII repeater mode in master slave operation. If you have slave operation, then you can have something different. Both of the slave, both are working as slaves. Okay. So both of the slave can be receiving the clock signal from the external oscillator, let us say 50 megahertz oscillator. So both are receiving separately same clock signals, and as you can see, both of them are utilizing two data lines of transmit signal and two data lines of receive signal, and we have receive data valid as well as receive transmit enable signal. So only 4 plus 2 6. So 6 lines are enough to have the slave configuration understanding. Now let us do one more operation, which is going to be MII signal. So we saw reduced MII, now we will talk about MII signal. So as you can see, in MII signal we have data signal of 4 bits transmit and 4 bits receive signal, right? Then we have transmit and receive signal control lines are transmit enable signal and receive data valid signal, okay? And then we have line status signal, which is nothing but CRS, that is your current sense signal. And we have or current sorry, this is called as carrier series signal. And then we have call, that is nothing but your collision detect signal, okay? So collision detect is actually utilized because let us say we are sending the or broadcasting the data, and at the same time if everybody is sending the data, then that will be collision and they will be waiting, they will be in waiting mode. We have error signal, which is nothing but your RX error. So these are the things that is utilized. So as you can see, we have phi is nothing but your Ethernet, and MAC is nothing but your, let's say, FPGA. So as you can see, between FPGA and Ethernet IC, these are the lines that is being used. Like we have transmit clock, then we have transmit enable, we have transmit data lines, then we have receive clock, then we have receive data valid, then we have receive error, and then we have receive data lines, and we have carrier sense lines or carrier sense signal, and then we have collision detect signal, okay? So this collision detect signal, so only how many, these many lines are being used to have the interfacing between your Ethernet physical layer transceivers, and at the same time we have, let us say, FPGA device which is acting as a MAC, okay? So we have how many lines, we can count it like 1 2 and plus 4, so 6. So 1 2 plus 4 7, then 8 9 10, 10 plus 4 14, 15 and 16. So total 16 lines will be utilized for the complete interfacing, okay? Now let us talk about next one, which is going to be RMII signal. So just now we talked about MII signal, which will be utilizing around 16 lines, okay, to have the interfacing between Ethernet PHY and MAC. Now if we talk about reduced MII signal, then here it will be only 2 plus 2 4 and plus 1 5 and 1 more 6. So total 6 lines will be utilized to have the RMII signal interfacing. So you can see we have Ethernet IC and then we have MAC IC here, right? So that is being interfaced like this. We have transmit enable coming from MAC to the PHY IC, then we have transmit data signal, that is 2 bits, and we have receive data valid, that is optional. If you want, if you want, you can remove this receive data valid. At the same time you can remove the receive data receive error signal also. Then we have 2 bits data, which is receive data bits, and then we have carrier sense data valid. And if you want, you can have both of them as reference clocks of the same kind, right? Let us talk about RMII master signaling. So this was a slave signaling. As you can see, the both of them, like MAC as well as my Ethernet PHY, both of them are receiving the same clock signal from the outside agencies, let us say like crystal oscillator or something else. However, if it is in master mode, then what will happen is like RMII mastering signal will be receiving like this, like clock will be sent from the Ethernet PHY IC to the MAC IC, so that MAC will be acting as a slave, okay? And this clock will be generated for the Ethernet IC through a crystal oscillator, okay? Now you can see RMII master signaling means only 2 data lines are used. So as I have already told you many times. So now we are in a position to understand that we have transmit enable, we have transmit data, we have received data valid, and we have received error signal. Then we have received data signal, and then we have carrier sense, sense signal and carrier, or carrier sense signal and carrier sense data valid signal. So these are the only signals that are actually utilized in your Ethernet PHY communication or Ethernet PHY interfacing for the Ethernet PHY IC and the MAC IC. Now let us say one more terminology that comes up is called as loopback. So if you want to test your Ethernet PHY IC through loopback operation or something like that. So let us say we have my FPGA connection, and then we have Ethernet block which is there from between this to this, okay? or you can remove the transformer. So between transformer and this MAC we have the Ethernet block. So this Ethernet block is having like media independent interface, then we have PCS, we have signal processing, then we have analog front end. All these things are there. Okay, so you can see like slowly one way it is going. So let's say transmit data signal is coming from MAC and it is going one way, and then after RJ45 there are loopbacks through two lines, which is like TD plus and TD minus, and then RD plus and RD minus, and then it will be looped back again, so that through receive signal you will receive it to the FPGA, and you will say that okay, whatever I had transmitted I have received it back, and this is how the complete testing has been done. So this is called as loop back. Okay, so this is very much used because of like we don't want to send the signal to the outside network while testing or while debugging our design. So in that case loopback test mode is very useful. And as you can see, we will be utilizing one transformer in the middle, which will be 1:1 transformer, and that will be actually utilizing as a AC coupled signal or isolation signal. AC coupled is basically used by putting capacitor here. If you do not need the isolation, then you can utilize capacitance. Okay, let us talk about typical application of this particular IC that we have studied till now. So we have almost studied almost everything. So let us say we have this particular IC, which is Ethernet PHY IC capable of giving you 10 Mbps and 100 Mbps data rate speed, right? Then we have DP83826 IC is capable of giving you MII as well as RMII interface capabilities to the MAC, which is going to be an SoC or ASIC or microprocessor or maybe like FPGA. So we have used a Spartan 7 FPGA to develop this particular interfacing, a Spartan 7 FPGAs. Now this particular IC needs power supply, so we will be generating a 3.3 volt power supply to power this up, and then we have a VDD IO signal, that is your IO supply, which will also be again 3.3 volt. Okay, we are not using 1.8 volt because 1.8 volt is lower voltage. Just to make sure it is very simple design, we have made it 3.3 volt itself. Another thing what will be utilized is there will be a magnetic that will be utilized, so you can utilize one transformer. I will tell you how does it look like. We have the magnetics that is there from, let us say, Worth Electronics or Worth Electronics I prefer, so you can go ahead with that. Then we have RJ45 connectors. These days RJ45 connectors are coming up with very advanced technologies having magnetics built inside, and like LEDs and all those things will be already there. We have LED status, so this LED status will be actually driving the RJ45 connector inbuilt LED itself, so there itself it will be connected. And then we will be needing clock sources, which either it can be 25 megahertz or 50 megahertz clock source. So this is the complete typical application that is there for the Ethernet PHY IC. Now let us talk about the magnetics that I was talking to you. So as you can see, this particular PHY IC will be giving you TD plus, TD minus, and then RD plus and RD minus signal in differential form. So these differential outputs will be going to get connected to the RJ45 connector to broadcast the data to the network, right? So what happens is this particular TD plus TD minus or this particular differential pair will be coming through the 1:1 transformer for isolation purpose, and this is how it is connected. So this particular connection will go ahead and it get connected, and then it is going to the RJ45 connection TD plus and TD minus. Okay, and the center tap will be grounded with capacitance, which is 2 nanofarad here, and as you can see this is matched to a one resistor which will be 75 ohm, and this 75 ohm is a match resistor or termination resistor, you can see. Similar to that, we have differential signal for RD plus, that receive data input also, so RD plus and RD minus, that is also going to go connected to the transformer, and this transformer will be getting giving you the output to the RD plus and RD minus, and this is also center tapped with 75 ohm termination resistor, and then both of them have been terminated through a 0.01 microfarad capacitor here. Okay, so this capacitor is actually utilized for, let us say, removing the spike or something like that, and it has a capability of like rating of around 100 volt capacity. And this is how it is called as also TPI network circuit, or maybe twisted pair interfacing between the Ethernet PHY and the RJ45 connection. Okay, good. So these were all about it. Okay, so we have seen this particular transformer. As you can see, this particular transformer can also be seen very easily by many of the manufacturers. So I have taken one of the circuit from the Worth Electronics. So as you can see, these are the transformers that will look like, and we have the connections very easy. These are the transformers which are 1:1. So you can see they are very much pointed out like TD plus and TD minus. So pin number 1 and 3 will be acting as like TD plus TD minus, and then TX plus and TX minus will be getting connected to your RJ45 connection. Okay, so this side is RJ45 connection, and this side is your Ethernet PHY connection. Okay, then we have RD plus and RD minus that will be connected to pin number 6 and pin number 8, and then we have like a middle pin which is acting as a CRD pin and then CTD pin. So that was nothing but these are the pins that is there, CTD pin and CDR pin. Okay, center tapped and receive and center tap transmit. Okay, so coming back to the right side, we have differential output which is going to be TX plus TX minus and then RX plus RX minus. This is very easy. So we'll be giving you the RJ45 connection as well, where it is connected directly. Now before that, we'll try to understand some more parameters that is there utilized. So if you talk about transformer applications, so you can see we have the transformers from, let us say, Pulse Electronic, that was suggested by this particular IC manufacturer, which is Texas Instruments. So these are the part numbers that you can utilize, and they have already tested with this particular IC, this particular transformer. However, we have also utilized from Worth Electronics, and that is also tested. You can see the turns ratio is having a just plus minus 2% variation, which is just 1:1, and then we have insertion loss up to minus 1 dB, and then we have return loss is minus 16 dB for this particular frequency range. For higher range, it is reducing to even lesser. Then we have differential to common mode rejection ratio. For 1 to 50 megahertz, it is just minus 30 dB, and then for 50 to 150 megahertz, it is minus 20 dB. If you talk about crosstalk, that will be nothing but like eye diagram and all. You can like try and see what is the crosstalk. So for 30 megahertz it is minus 35 dB, and for 60 megahertz it is just minus 30 dB. Okay, let us talk about capacitive DC blocking. So what happens is, sometimes you don't want to utilize a transformer to reduce the cost, or like if suppose your application doesn't need any isolation, then you can remove the transformer, and you can simply have a DC blocking capacitor in the middle. So this TD plus and TD minus differential lines or differential pairs can be directly sent to the RJ45 connector through a DC blocking capacitor of 33 nanofarads. Okay. Similar to that, RD plus and RD minus differential output lines can be sent to the RJ45 connection by a DC blocking capacitors of 33 nanofarads. So this is also called as transformer-less DC blocking configuration. So transformer has been removed from the interface between your Ethernet PHY as well as the RJ45 connection. If you talk about crystal connection, so if you see crystal connection, what is going to happen? If you are going to give a clock signal from the crystal, then crystal will be used. Let's say piezo crystal or something like that, it is being used, and then Xi and XO will be pins will be utilized for generating the crystal oscillator. So you can see a typical frequency must be 25 megahertz, and the frequency tolerance must be minus 100 to plus 100 ppm. Okay, so this should not be varying based on the temperature variation, so it should be very good. So this is called as also like operational temperature, aging and other factors will be just plus minus 100 ppm maximum. We have load capacitance. Typically it is taking 15 picofarad, and then you have equivalent series resistance of 50 ohms. Now let us talk about the power supply. So power supply is very important. So as you can see, we have VDD IO pin. So in VDD IO pin you will be requiring to put like these capacitors. So let us say like IO supply was 3.3 volt logic level or 1.8 volt logic level. So you will be requiring to put one ferrite bit, which will be like FB, that will show you during the circuit design. However, you can have these understanding so that you don't make mistake during the circuit design. And then you have to put capacitance like this, like 10 microfarad, one bulk capacitor, then 1 microfarad, then 100 nanofarad and 10 nanofarad. So these are the 4 capacitors that will be required to put at the VDD IO pin. Coming back to the supply pin of AVDD 3V3, so there also you will be requiring the same amount of capacitors and then supply voltage plus one ferrite bead for removing the EMI/EMC noise. Okay, so this is the power supply decoupling recommendations. Now what happens is, actually it becomes very important for the design perspective, that circuit design is not much critical. For Ethernet design or Ethernet like circuitry, your board design becomes very important. So if you talk about layout guidelines, so in this case you can see we have layout guidelines given by the datasheet itself. So in signal traceage, if you see, this is the thing that you should follow. Okay, so does not maintain parallelism, means this particular line should not be this one. Okay, so this is wrong. So this is the one which is going to be correct one. Okay, so that is the thing that you have to follow. At the same time, there should not be any stub or something that is coming outside, so it must be removed. Okay, so this is also to be removed. So this is the way you can maintain a parallel line. So this is also called as like differential signal traces. Okay, now coming back to the stack up. So sometimes a stack up is also there. So if you have just 4-layer PCB, then we have ground, then high speed signal. High speed signal will be nothing but your Ethernet lines, and then we have VDD supply, which is little bit faint. So you can see we have 4-layer board. So in 4-layer board we have the high speed signal on the top and bottom, and then we have ground layer and then power supply layer. So this is your top layer, this is your ground layer, and this is your power layer, and this is your bottom layer. Okay, so for 4-layer board it must be stacked up like this. If you have 6 layers, then you can insert your data lines or your high speed signal lines stubbed between. Okay, between the ground and power. So this is the ground layer and this is the power layer. So between that you can stub them. Similar to that, we have 8 layers. So it becomes much easier, because we can go through and have a ground layer and power layer separately, and in between you can have the signal layers. Okay, so these are the recommended stack up that was there. Coming back to the layout example that was given by this particular data sheet. So we have the PHY IC, that is your Ethernet PHY IC, then we have transformer, and then we have RJ45 connector, and that's all done. RJ45 connector will be actually chassis grounded so that it avoids any EMI/EMC issue or ESD problems. Okay, and this is the digital ground that is there. I'll tell you one thing, like there was a design that is already there by the a Texas Instrument itself for this particular IC. So what we'll see is let us try to understand a few things that we should understand in this particular session. So you will be needing a power supply design. So power supply management, what happens is, let us say we have the input voltage range from 5 volt to 12 volt. Either you can give it from the USBs also, as well as like a adapter, power adapter, or maybe battery. So there we can generate one switching regulator with 5 volt output. So switching regulator is going to generate your 5 volt output, and this 5 volt output can be utilized to generate through one linear regulator for 3.3 volt output. So these two voltages will be utilized. Okay, and as you can see they have already developed one very nice evaluation board for this particular IC, which is DP83826. and if I open this particular link, then you can see we have a DP83826 low latency 10 Mbps 100 Mbps Ethernet PHY evaluation module. And this is very good IC, and they have given you almost everything. This is the particular boards that is like looking like, so different views are there, and it costs just 149 USD. So if you want, you can directly buy this. If you do not want to develop your own board, just for evaluation purpose, you can quickly go ahead and do that. Anyway, we have already developed the complete circuit for our like design, so I will be explaining you that thing for your complete understanding. However, for right now, for understanding purpose, I will take this particular example to give you a quick overview about this particular design. Okay. So this is the particular board that is there, which is like connected properly, and as you can see like different understanding. So we have the power supply, which is like 5 volt to 12 volt, and this ground. So this is the power supply block, power supply input that is coming. Then we have straps and LEDs. So these are the LEDs that is there, 4 LEDs are there. Then we have MAC interface, is nothing but going to go to your FPGA connection. Okay. Then coming back to the magnetics. So this is the like magnetic that is used here, from Pulse Electronics actually they had used. And then this is the RJ45 connector that is there bottom side. Okay. We have one USB connector also that is there utilized here, and we have clock generator. This is going to utilized as a clock generator, and this is the PHY IC that I am going to talk about, which is going to be DP83826. Okay, so this is the PHY IC that is there. So this PHY IC will be actually used in between. How it is used, so that you can very easily see. This is the MAC interface, this is the PHY IC, this is the transformer, like 1:1 transformer, and then this is the RJ45 connector that is going to send this signal to the network, right? Okay, so these were all about this like board. If you want, you can have a look, a proper look. So this is the nice view about it, and then this is bottom side view, which this is the RJ45 connector that I was going to talk to you, RJ45 connector, and this is my USB connector that is used for maybe like power supply, as well as like we have power supply adapter as well separately. Okay, so these were the things. Now let's talk about the circuit that is actually done. So if you see, very nicely arranged, this particular 4 transmit data lines are there. So TXD0, TXD1, so that is there. Coming back to the like voltage supply, so this VDDA 3.3, how it is used. So as it was suggested, these are the decoupling capacitor that is used, and then we have one like 0 ohm resistor, just for the purpose of like giving a little bit of impedance in the middle. If you want, you can put a ferrite bead for this, so that you can make it much better. Okay. Similar to that, these are the decoupling capacitor that is used, like 10 microfarad, 1 microfarad, 0.1 microfarad, and 0.01 microfarad. Okay, with VDDIO, which is again 3.3 volt. If you want, you can change the level to 1.8 volt also. There was a possibility in this particular evaluation board. Okay, then coming back to this differential lines. So RDP and RDN is nothing but your positive and negative line, which is going to get connected to the transformer. After that, it is going to get connected to the RJ45 connector. Similar to that, we have differential transmit lines. So this is the differential receive lines, and this is differential transmit lines. We have transmit data lines to the MAC, okay, like FPGA, and then we have like C external. So C external is nothing but a capacitor that will be grounded. Then we have management data IO lines. So management data IO lines is not used here, so it is just pulled up. This is your MDC clock, that is your management data clock. Okay, we have reset switch also. So reset switch, if you want to reset this particular Ethernet PHY IC, then you can press this particular switch to reset this IC. Coming back to the receive side, so we have all the control lines and receive data lines. So you can see we have receive data valid, then receive data signal, that is D1, D2, D3, and D0 will also be there. Okay, then we have transmit clock, we have a collision detection, then we have carrier sense lines. Okay, and then we have LED 0, clock out, and we have, yeah, here it is receive data 0 line, right? Then we have clock output line, that is your XO, and then we have clock input line, which is your XI. Okay. Coming back to the magnetic, so as you can see, this is the magnetic that is used. As you can see, TDP and TDN is used. The transmit differential lines through the isolation transformer, 1:1 isolation transformer, and this isolation transformer sending the data to the RJ45 connector. So this is my RJ45 connector, and you can see transmit data lines are at differential lines are at pin number 1 and 2. Okay. Then if you talk about receive data lines, so receive differential lines are RDP and RDN, so they are getting connected to pin number 3 and pin number 6. Okay, so pin number 3 and pin number 6 can be used for this purpose. Then if we talk about the input side, we have this capacitors which is getting grounded, so that is center type capacitors. For the receive signal differential pairs also we have the center type capacitors here. Then at the output side we have matching resistors, so that is termination resistors, which is 75 ohm for both transmit differential pair as well as receive differential pair. So 75 ohm, and then they are AC coupled with 1000 picofarad of 1000 volt rating. Okay, so 1 kV rating of capacitors to the chassis ground. So this is your chassis ground, which will be actually connected through the RJ45 connector chassis ground also. That is nothing but your earth ground. We have pin number 4 and 5 and pin number 7 and 8. So these are actually used for high data rate. We will be having more number of differential pairs. So right now we are using with 10 Mbps and 100 Mbps. That's the reason they have been terminated with a resistor of 75 ohm each. Okay. We have LEDs, so LEDs were not inbuilt in the RJ45 connector. So here you can see we have LED 0, we have LED 1, then LED 2 and LED 3 are there, right? So these 4 LEDs are there, which is being used for the purpose of status. And then at the same time, only one more thing that we do always for this particular transmit differential line and receive differential line is we protect them for the ESD also. So for ESD protection we try to utilize ESD diode. So this is the ESD diode that is used for your transmit differential pair and receive differential pair lines, that is TDP and TDN and RDP and RDN. So this is the particular ESD diode that has been used in these many pairs. So this is having one pair and one more pair, so 2 pair of ESD diodes are there in only one IC. So alright guys, hope you have a good understanding about this particular IC Ethernet PHY schematic design. Now we'll try to give you a complete understanding about our own design and implementation and how this particular IC has been used in our application and what are the different techniques to design the transformers and this particular RJ45 connector and how to connect interconnection interface through the FPGA. So that is the main important thing, like connecting all these pins to the FPGA will be taught to you in the next session. Thank you so much. If you do have any queries or any questions regarding the Ethernet connections or Ethernet designs, then you can put down your queries in the comment box and we shall be able to give you answers as soon as possible with proper explanation. And learning this particular Ethernet design will be a quite good understanding and it will give you a very good skills in hardware design engineering. So what we will be doing in this particular session is we will try to give you almost 3 ICs, like there are different high speed ICs as well for Ethernet physical layer transceivers. So those also we'll try to include in this particular session. Thank you so much.